Right, today's topic is about geodesics. Now, there are many ways to define geodesics. Okay, depends on the textbooks. Okay, then what definitions are equivalent at the end. Okay, I'm not going to use the same definitions in textbook. There are some reasons here. Okay. So let's have a quick review about what we learned about curves on the surfaces. So we have a surface. This is S, and that's a curve here, right? Okay. So we assume that gamma, okay, it's from A to B. The interval, right? This gamma S has unit speed. Okay, so that means the length in the space is always equal 1. Okay. Then we see that see that first of all, this is a tangent vector, right, to the surface. So let's draw this. This is a tangent vector. And we also know that for the tangent plane, we have a normal vector n, right? Right. This is already pre-existing. So then you can get a frame. That's called n cross a gamma prime. So you have an orthogonal frame. Okay. So this is around this curve on the surface. There's a natural orthogonal frame there. Okay. So any vector can be a linear combination of those three vectors. That's okay. So now let's take a look at the derivative. Okay, because this is always equal 1. So when I differentiate twice, I get 2. When differentiate this, I get this, right? So what does that mean? That's gamma prime S is perpendicular to this. Okay, so let's go back to this picture. This is gamma prime S. This is a normal vector n, and this is the cross product. Okay, so we have a plane perpendicular to the tangent vector to the curve. That plane is a linear combination of those two vectors, right? So gamma prime x can be written as, gamma prime s, it's perpendicular to the tangent vector. So it's something like that, the gamma prime s. So this is in the plane perpendicular to the tangent vector. So this can be written in the combination of ns plus kg s and ns plus gamma prime, right? So this is called normal curvature. This is called geodesic curvature. So there's a reason why it's called the geodesic curvature. Okay, and we know that for the normal curvature, this can be actually the value of the second fundamental form in the direction of tangent vector at the point. Okay, because at every point there's a normal vector, the second fundamental form there, right? Second fundamental form is a bilinear form, right? It's a bilinear form. Okay, it's determined by the normal curvature. Okay, if you choose a the opposite direction of the normal vector, then you get a negative sign. Okay. So that's only this, that depends on the normal vector, the choice of the normal vector. Okay, so we already studied this, right? And then using surface patch, then you can compute the normal curvature of the curve using the LMN, the coefficients, right? Yeah. So I'm not going to spend time on the normal curvature. So today we're going to focus on the geodesic curvature. Well, if you look at the identity, above identity, if you view the curve in the space, three-dimensional space, then the length of this, see, remember, this is called the curvature. Okay, this is called, we already have the curve. This is called the curvature of the gamma in this three-dimensional space. Okay, so if we view gamma as a curve in three-dimensional space, not only just a curve on the surface, then that is actually the curvature, okay, by definition. Then you have a torsion, remember, right? Then you differentiate again, then you get a torsion, okay? So the torsion can be related to the normal curvature, maybe geodesic curvature. So we can discuss a little bit later, okay? So this is a normal curve. So now based on the above identity, right? Based on the above identity, okay? Based on this identity, I can quickly get this this formula. Okay, so the curvature square, our square of the curvature is going to be the square, the sum of the square of the normal curvature and the geodesic curvature. Okay. All right, so here's the definition. I'm going to use the geodesic curvature to define geodesics. Okay, a curve gamma, a unit of speed, a curve gamma. Okay, yeah, a curve on the surface is called a geodesic if its geodesic curvature is going to be zero. Now, the geodesic curvature is defined using the arc length, but you can also get a formula to compute the curvature without using arc length. Okay, so we can take a look at the previous formula. Do we have the formula there? I think so. We have the formula without using arc length. Okay, so here's the formula. Okay. So yeah, so how to compute it? Yeah, so it's important, right, to decide whether the curve is a geodesic. You have to compute the geodesic curvature. But the geodesic curvature, the formula, original formula is given is using the unit. Step one, you parameterize the curve by the arc length. Then it's given by this formula, right? So then you can compute that this is gamma double prime s and s gamma prime s. Okay, so the geodesic curvature, okay, if gamma s is, if gamma is parameterized, I should, yeah, if I put the parameter there. If gamma is parameterized by the arc length s, then curvature is going to be gamma double prime m gamma prime. Okay, Now, if it's not parametric by arc length, this is exercise 7. Exercise 7.3.1. I did not assign to you, but that's a formula. Okay, for in general, okay, if T is a parameter of gamma, okay, then it's not necessary to be arc length. Then the geodesic curvature can be still have the same formula, because this is going to be gamma prime and 3/2. Okay. So it's not necessarily a unit speed. Okay. So the formula is pretty similar. Okay. The formula is pretty similar. The reason is, okay, think about that. The reason is as follows. Okay, let me do the exercise here. Finish the computation. So gamma, right? So first of all, it's parametered by T, then it's T, right? It also can be parametered by S, depends on which parameter you're going to use. Okay, S is a function of T. So gamma prime T, so S is S of T, right? That'd be d gamma ds, ds dt, right? And the second derivative is going to be, okay, plus gamma ds d squared dt. Okay, so that is formula. So now let's take a look at gamma double prime and okay. So here we use actually use a t, right? So let's put a t here, t here, t here. So using the above formula, I do have a gamma square gamma ds square ds dt square. Okay. All right, so here's d gamma ds and then ds dt, okay? And this will be, I think, yeah. I should, yeah, my notation is wrong here. Yeah, I should write the norm. Okay, so that will be the norm. Okay, so that is going to be d gamma ds and ds dt and cube, right? But S is the arc length, that's why it's going to be 1. Now, when you multiply this out, this will be 0. The reason is n cross d gamma ds is perpendicular to the tangent vector. So the dot product with this is going to be 0. So what you get here is dot product n d gamma ds and then ds dt and the cube. And the denominator, you also have ds dt cube. So that canceled out. That's why I get the gamma ds square dot n. Okay. So that is the origin definition. That is a geodesic curvature point S. But you can compute it using this more general formula. All right. So so as you can see that, so from this above formula, right? And so what you can conclude, the geodesic curvature must be 0. Okay. So the geodesic curvature must be 0 if and only if, okay. So KG 0 if and only if, okay, gamma double prime t, the dot product n. Right? So if and only if gamma prime is perpendicular to this. Okay, so let's go back to the picture again. This is gamma prime t, and the normal product. This is a normal product, right? And this will be the normal. Okay. So gamma double prime is going to be perpendicular to this vector. Okay. So this means gamma double prime. Now this gamma, this projection. You see, this is could be somewhere like that. Okay, this is gamma double. So there is a this must be in the plane spanned by these two vectors. Okay. Okay. So in other words, gamma double prime must be a linear combination of n plus d over t gamma prime t. Okay. So you can use that to define you can show that a curve whether it's whether this is going to be now given arbitrary given curve with arbitrary parameter to check whether this is a geodesic, means the corresponding geodesic curvature is 0. If only for the second derivative must be a linear combination of this. Okay. T is arbitrary parameter. You can check that. Okay. And now, do you remember the covalent derivative along the curve? Okay. So that was a covalent derivative. And let me use a notation here. Yeah, you can also, you see along the geodesic, the tangent vector itself is a covalent derivative, right? So consider, so let gamma t be a curve on the surface, right? Then gamma prime t is a vector field, right? Itself a special vector field along gamma, right? Yeah, now we remember we have suppose you have a gamma, right, on the surface. And if you have a general vector field, right, how do we define its covalent derivative? The covalent derivative is defined to be that's our notation. So covalent derivative, let me check whether this is required. It's just a curve, okay? It's not necessarily to be unit to speed. Okay. So gamma, a vector field, right? This is defined to be the derivative, okay, and the projection onto onto the tangent plane. Okay. So VT is going to be tangent vector. Okay. Then okay. Right. So VT is V prime T. Yeah. So that means we only consider when you differentiate in the usual sense, and then you have two parts. Okay. So when you differentiate, then along the geodesic, right? So this is there's a part. This is actually another tangent effect on this. Yeah, this is for an arbitrary vector field. All right. Now, if you want to look at this covariant derivative of the tangent vector field, okay, this is going to be gamma double prime minus gamma prime t and n and n. Okay. So, well, slightly different. Okay, we have if it's a geodesic, okay, if only if you have this identity. Okay. So for geodesic, so if gamma prime t is a geodesic, is a geodesic. So what do we get? The covariant derivative. Okay, so that means gamma prime double prime t is going to be a over t gamma, right? And plus b over t gamma prime, right, along the geodesic. So from here you can tell that A is just the projection, right? So that's going to be an A over T. Okay, and gamma double prime dot gamma prime T. Then you have to be careful. This is the length of gamma prime T squared. Okay, slightly different. Okay, that's for B. Okay, so this part is just L, right? So if it's a geodesic, then you have this identity. Okay. So that means gamma double prime equals, okay, gamma double prime t and n t, t plus b over t gamma prime t. Okay. So the difference is going to be b over t. Okay, so that means okay. So for the geodesic, you have this property. As a derivative of the vector field along the geodesic is in this form. Now conversely, maybe this is also true. If we have a curve, the derivative is in this form, and or the derivative of geodesic field. Now, can you prove that it must be in this form? Okay. So we're trying to get, so now we assume And now we assume that assume that a gamma t satisfies for some B of t. Now, according to the definition, this is nothing but gamma double prime t minus gamma double prime t of n. Okay. Right? So that implies gamma double p is okay. So that's it. So this is a geodesic. So now we conclude the following result. We call the proposition. Okay, gamma t for an arbitrary parameter is a geodesic if and only if, right, by definition, right, geodesic curvature 0, okay, if only for gamma double prime equals A over T n T plus B over T gamma prime T, if and only if this gamma prime gamma is going to be B over T gamma prime. Okay, so that is those are the equivalents. Okay, so by definition, that means the geodesic curvature 0. Okay, so we can use that to prove whether a curve is geodesic or not. Okay, now let's take a look at some examples. Section. Now in the book, because the definition is slightly different from mine, so that's why there's another proposition that any geodesic has constant speed. I don't like this. Okay, so we define a curve to be geodesic. It should be independent of parameter. Okay, so that means we should use, in my opinion, if I wrote this book, a curve is geodesic, then as an object, right? As an object, so that should be independent of choice, so particular parameterization. So a curve, okay, that is image of some map, okay, is a geodesic. The curve C is a geodesic if there's some parameterization, that's enough, not necessarily that counts, such that the second derivative as a geodesic curvature. The geodesic curvature is independent of the choice of parameterization. Okay. And then if you use a special parameterization, then you should have this properties. Okay. That is after the T here. So now let's try to see a straight line on the surface must be geodesic. Let's look at it. Okay, let C be a straight line. On surface. So if we on surface S in R3, okay, then C is a geodesic. Okay. So if you see there's a straight line here, straight line and the surface, okay, it's harder to draw, yeah. If there is a straight line here, this must be a geodesic. Okay. How do you prove that? So geodesic curvature must be 0. So you just need to verify one of these two conditions. Okay. So let gamma t, because it's a straight line, so it's a vector A t plus vector B, right? You know, you can parameterize. Then the straight line can be always parameterized like that. Okay. And then the second derivative is going to be 0. Of course, this is going to be A over t n t plus b over t gamma parameter. Okay. Of course, for A over t equals 0, B over t equals 0, right? So that's why based on the above theorem, and therefore gamma is a geodesic, okay. Or the C is geodesic. Okay. Yeah. We find the parameterization for the C. So this is a so that's a C is a geodesic. Yeah, more precisely, a geodesic should be a curve on the surface, but we don't want to measure any parameterization. Okay. Okay. So that means there is a parameterization such that the geodesic curvature is. Now, the geodesic curvature is independent parameterization, honestly. Okay. But you can describe it using parameterization. Right. Either the normal curvature or geodesic curvature. They're independent of parameterization. Okay. So this is a curve. As long as for some parameterization, if it can express in this form. Okay. So I have to make a comment about the curve, right? A curve on the surface. Okay. You can use a arc length to find the parameterization. Then you compute it. Okay, the second derivative. Then you get Kn and Kg. Okay, so those are the curvatures. It's really an independent choice of special parameterization. Okay, that's my remark. So have a surface, have a curve here. I usually denote by C. Then you find the parameterization gamma, and the gamma prime S is going to be 1. Then the second derivative is going to be Kn, S, and S, and the KGS and S plus, yeah. Okay. So these two numbers as independent of the choice of parameterization. So KNS and KGS are independent of the choice of a gamma. Okay. But actually, there are not much choices here because it's, S is arc length, right? So it's independent, almost a unique choice here for gamma. If we want to let S to be arc length, the only difference is another gamma, maybe S is S minus another constant. Okay. Those are the, yeah, gamma S is almost unique. Okay, if this is your starting point, this is S. Okay, that's a unique gamma S. Okay, it's not easy to find out. Independent gamma. Okay, but there are not many choices, you know. If you have a two parameterization, then the difference is just by shift of the variable s. All right, so the so-called normal curvature and geodesic curvature of the curve at this particular point, you can choose a parameter, you can choose a map gamma to compute, and even the parameter is not necessary to be unit speed, right? But in the definition, right, the geodesic curvature is defined using a parameterization with a constant speed, with unit speed. Okay, but that if that should be independent choice of particular such parameterization. Okay. The difference is if this is another parameterization, comma theta s, right? There's not essentially it's the same almost. So gamma s maybe just equal to gamma s plus some lambda. Okay. Yeah, depends on where you start. Right, so it's easy to see that a strict line is a geodesic on the surface if you see it. So if you have a bunch of so let's take a curve, right? So you have this is like a fence, okay? So this is surface. You can see all those strict lines, and they are going to be a geodesic. So this is a surface, okay? It's let's parameterized by this u, and this is a gamma u, okay? And this is those are another vector delta u, right? So gamma uv is going to be gamma u plus v delta u, okay? Right? So for fixed u, so you get a strict line. Okay. Then for any fixed u, okay, and C over V, which is defined as sigma u v. Okay. Okay. So that gives you, this is a strict line. S, right? So it is geodesic. Okay, so it describes a geodesic. And it is a geodesic. It's a unit, it's not a constant speed geodesic. Okay, C is called a constant speed geodesic. Because then we're not going to distinguish between a map for the curve and the curve when you're talking about geodesic. Okay, sometimes we say this curve on the surface is geodesic, sometimes a map which describes that curve is called geodesic. Okay. So all straight lines in the plane are geodesics. As are the rulings of any road surface. Okay. Another problem here, let's look at the example. Okay. Consider normal section of a surface. Okay. Normal sections of a surface. What is a normal section? Right, by definition, a normal section Yeah, a surface, first of all, that's my claim, geodesics. Okay. Normal section by definition is going to be the intersection. A normal section is an intersection of a plane with a surface. Okay, the plane has the following property. Having the following property. Is right. It is perpendicular to the surface at every point, at every intersection point. It is perpendicular to the surface. And not every surface has every plane has this property, right? So this is a surface, right? If you just use a plane to cut it, right? This is not going to be the normal vector in general, right? Because this is not going to be perpendicular to the tangent plane. So this is a tangent plane, right? The tangent plane, those two planes are not necessary to be perpendicular. Yeah, how do you define two planes perpendicular, right? So there are two normal vectors are perpendicular. All right, so let's look at this. Why this is so this is intersection, right? So we parameterize by gamma, right? We can assume it's a unit speed, okay? We assume that for the simplicity, we assume that's going to be 1. All right, so first of all, gamma is a plane curve, right? First, gamma is a plane curve. Okay. And this is we call it pi. In pi, right? Plane curve, so that's why this is a gamma prime, right? So gamma double prime will be still in the plane. So gamma double prime, okay, because plane curve. Okay. So gamma double prime and the gamma prime, okay, are in the plane. Okay. Now, by assumption, pi is perpendicular to the tangent plane. What does that mean? The normal vector to the pi should be perpendicular to the normal vector of tangent, right? So we are, by assumption, right? We know this is perpendicular to tangent plane at this particular point, right? So that means gamma double prime, right, cross product. This is normal vector to the plane. It's perpendicular to the normal vector, right? Okay. So why is the geodesic curvature 0 in this particular case? Look at the geodesic curvature, right? That's K and S. This is going to be NS plus gamma prime S. Okay. So gamma S prime plus gamma prime S, right? Right. Plus now actually what is this vector? This is a think about this is a gamma prime. This is a N. Right. The product of these two will be going that direction, N plus gamma prime. Then you do the cross product between those two again. So you actually get the negative N. Okay, so that means yeah, but we know that this is going to be perpendicular to, right? It's perpendicular to NS implies KG must be 0. So that's why it's geodesic. But that's good. You know, if you have a plane perpendicular to, yeah. So let's look at example, special example. Okay, cylinder. Okay. Not a necessarily circular cylinder. Maybe a cylinder something like that, right? Okay, so this is cross product. Okay. Now, is this a normal section? This, you know, the normal vector to this surface, okay, to this cylinder. This is normal vector to the cylinder, okay, but normal vector to the plane. So is this one, because they're always perpendicular. Okay, so that's why this must be a geodesic. The intersection must be a geodesic. Okay, this is a geodesic. Okay, the reason it's a geodesic is the intersection of a plane and the surface. Okay, and the normal vector of the surface at that particular point is always perpendicular to the normal vector of the plane. Okay. So those are the easy observation to see the geodesics. We can also take a look at another problem. Here's a cone, right? This is a cone. Okay, take a look at this cone. I think this is a geodesic. Those strict lines are geodesic. Okay, those are the lines because it's a strict line. Okay. Now, but this one may not. It's not going to be geodesic. Okay. It's not necessary to be geodesic. Okay. Okay. So you wanted to get a geodesic on the cone. Your plane must be perpendicular to the surface. Okay, so I have to look at this cross section like that. Okay, so that the normal vector. Yeah, it's harder to describe. You have to find the right angle to cut this this cone, so that the cone at every point, the cone is perpendicular to the plane. Do you think it's possible? Maybe it's impossible, right? So we are not going to use this method to find the geodesic in general, because it's almost impossible to find a special plane to use it. But one more example I'm going to look at. How about the surface of evolution? Yeah. So can we find some geodesics on that? Okay, surface of evolution, right? And there's a strict line here. I'm pretty sure this one in the middle here is going to be a geodesic. So if we cut it, the normal vector to the surface and the normal vector to the plane you're going to use to cut it is going to be perpendicular, right? This is the shortest loop in the neck. So this is going to be a geodesic. Okay. How about, let's try the other cut. Okay. How to cut? Let's cut this one. I'm going to cut it in the middle. Okay, let me draw the picture. What I'm going to do, I'm going to cut this. Okay, cut through, right? So what I got here is I'm going to get curve. I'm going to use a red line. So do we think this is going to be, this is on diameter, okay? This is center. So what is is this plane is perpendicular to the surface at every point. Yeah, this is a normal vector to this plane, right? Right, what is the normal vector to this plane? I'm pretty sure the normal vector to this to the surface at that particular point lies on the plane. If you can show that, then that's a two perpendicular, right? Can you see that? Okay, so the normal vector to the surface at that particular point lies in the plane, okay? Right? Lies in the plane. If you can see that, then this is a geodesic. This is a geodesic. Okay, so because the normal vector lies in the plane, of course it's perpendicular to the normal vector to the plane. So that's why the plane perpendicular to the surface. Two surfaces we say perpendicular to each other because it's the normal vector perpendicular. So on the surface of a revolution, you will see that the curve you're going to use to generate the surface is a geodesic. And the shortest closed circle on the surface is also going to be the geodesic. Okay. Now, the geometric meaning of geodesic, using geodesic curvature, you can say geodesic. What's the geometric meaning? The geometric meaning we're going to understand is geodesics are locally minimizing curves on the surface. Okay, so that means if here's a surface, this is a geodesic, that means for a small neighborhood, any other curves are going to be longer than that particular one. Okay. This should be the original definition. Locally minimizing curves are called geodesics in some textures. Then they show that if and only if the geodesic curvature is zero. Okay. Locally minimizing means for sufficient short piece of curve, then all the curves join these 2 points, and the points are longer than that curve. So that's why it has a minimum length. Okay. So if you want to go from one point to another point, the shortest path will be the geodesic. Okay. But then maybe there are many geodesics there. And we're talking about, they sometimes call it global minimum geodesic, minimized curves. For example, the sphere, right? On the sphere, the north pole to the south pole, there's so many great circles passing through. Okay. All of them are geodesic. So geodesic between 2 points are not unique. Okay. But if the point is here, then if the point is here on the sphere, okay, on the sphere, this is sphere here. So you draw the great circle around that. Okay, this is a geodesic. Okay, from P to Q, the shortest path from P to Q is going to be the portion of the great circle. But you can also go around here from here to here, right? This is also geodesic. Okay, but it's only locally minimized. Okay, it's not globally, it has a minimal length because they are another one shorter than that. So we are talking about this a little bit later. Now, next class, we probably is going to find equations, how to give a direction, how to find the unique geodesic going out of that direction. Okay? So geodesics is a very important topic on the surface. Right. I'm going to stop here, so not much. Yeah, this section will be short, much complication.